My next part of 4-3 is called conditional probability. You will use a conditional probability every time you have dependent events. Now the formula that I'm going to write down for conditional probability looks very similar to the one that I've already written down for multiplication rule in the case of the events are dependent. Now remember, dependent events means that the probability of B is affected for the fact that the event A has already happened. So what I'm doing, let me go back over here. What I'm doing is I'm essentially solving for the conditional probability. So this part, I'm pointing right at this piece right here. So this part is called the conditional probability. It's the probability B condition A. So if I divide both sides by the probability of A, I'll end up with a formula that's solved for the conditional probability. So the formula right here looks like this. The probability of B given A is therefore the probability of the intersection, meaning what happens if they both occur at the same time, divided by the probability of that other guy, the one that already happened. So one of the examples that's in the book, I'm going to start with 4-32. A box contains black chips and white chips. A person selects 2 chips without replacement. So as soon as you hear without replacement, you want to say it's a conditional probability. If the probability of selecting a black chip and a white chip, so they're giving me the probability of selecting a black chip and a white chip. Now that probability is given to me at 15 out of 56. Great. And the probability of selecting a black chip on the first draw, so the probability of getting a black chip, is 3 out of 8. Find the probability of selecting a white chip on the second draw, given that the first chip selected was black. So let me write that down in probability probability notation. Find the probability of selecting the white chip. So I need the probability that the white chip was selected on the second draw, meaning that something has already happened, given that the first chip selected was black. Okay, perfect. I need this. You want to write down the formula. It's the probability of W and B at the same time divided by the probability that the event B has already happened. This guy right here. If you can't see where I'm pointing, I'm going to point right here. So this is my second one, the one that has already happened. So the probability of B. And coincidentally, this is a book. This is first semester of statistics, so everything that you need will be given to you in the problem. So conveniently, we were given the probability of the intersection, and we were given the probability of that first event happening. All it is just a little bit of work with a calculator. You take 15 out of 56, divide that by 3 over 8. Either decimal approximations or fractions. I have 5 over 7 as the fraction, or 0.714 and then 28, so I'll round this up to a 3. Okay, great. So if the information is given to you using the notation, the best way is to approach the problem using formulas. My next example, 4-34, has a two-way table. A recent survey asked 100 people if they thought women in the Army force should be permitted to participate in combat. The results of the survey are shown. So we asked males, we asked females a question. The answer to my question was either yes or no. Out of men, 32 answered yes, 18 answered no, for the total of 50 people, or 50 males. Out of female, 8 said yes, 42 said no, for the total of 50 females. Now what you want to do is you want to continue this two-way table and get the other totals. That means that 40 people said yes and 60 people said no, for the total of 100. Notice, if you add up the rows, 50 plus 50 is 100. If you add up the columns, 40 plus 60 is 100. So this grand total is represented right there. From a two-way table, I can ask you a bunch of different questions, and some of them are given to you in the book. Part A. Find the probability the respondent answered yes, given that the respondent was a female. So, the probability that they're asking us for is the respondent answered yes, given that we're only talking about females. You can use the formulas, meaning you need to find the probability of yes and female divided by the probability of female. So I'll do it using formulas first, and then I'll show you a shortcut looking at the two-way table. So if you're looking at the intersection of yes and female is right here. No, right here. The yes and female, there's 8 of them. So the probability of the intersection is 8 out of 100. The probability of getting females, well, there's 50 females. So those are my females, so this is the number that I'm looking at. 50 out of 100. Notice the fractions, and I'll actually work through the fractions. 8 of 100 times you flip the other one. These two cancel out. You end up with 8 out of 50. Now the shortcut is right here. When you are given that we're only talking about females, what you're doing is you're only concentrating on row number 2, as in everything else doesn't exist. Your grand total is 50 because you've already selected females. You actually don't care how many males you have at all, and you're interested in that yes female out of the females. So you can just take a look at this 8 divided by 50, and you will get exactly the same answer. If you'd like, you can give me an approximation using a decimal. Part B. The respondent was a male, given the respondent said no. So I need the probability of a male, given that we're only talking about no people. So I'm going to take another highlighter and kind of highlight this part. I'm only talking about no people. So if I'm talking about no people, I know that the bottom has to be 60. Now I need males out of those. So there's my final answer. You probably want to reduce that just a little bit, and I'll actually use my calculator to get a decimal approximation. 18 out of 60 is not an approximation, it's 30%. My last concept in 4-3 is probability for at least. Now what we're dealing with is at least one for most part. I'm going to take a look at example 4-35. A person selects 3 cards from an ordinary deck and replaces each card after it is drawn. Find the probability that the person will get at least 1 heart. Okay, so card is drawn and replaced. As soon as you hear the word and replaced, we do not have any conditional probabilities. This does become a much easier problem at this point. I am drawing 3 cards and I need to get at least 1 heart, meaning I can get all 3 hearts, or maybe I can get a heart first and then 2 non-hearts, or maybe I can get a non-heart and then 2 hearts after that. So there's actually many different possibilities of getting at least one somewhere. If you start adding all of those probabilities, chances are you will get lost and forget something at some point. What we're dealing with at least one is a complement. The complement, meaning opposite of at least one, is getting no hearts. So I'm going to write this like this. My event E is at least 1 heart. There's many different ways of getting at least one. So what I can do is I can organize a different event, which is E complement, meaning no hearts. Now the complement has only one possibility of happening. So the probability of E complement is if I need a non-heart in the first draw, it's 39 out of 52. Because 13 are hearts, that means that the other cards out of the 52 is 39. I just took 52 minus 13. I got my 39. Now, if the card is replaced and reshuffled, I have a brand new deck. It's still 52 cards. There's still 39 non-hearts. So getting the second non-heart is 39 out of 52. Getting the last one is exactly the same thing. So all I'm really doing is taking out my calculator and 39 out of 52 raised to the power of 3. I'm approximating to 4 decimal places, so 0.421, and then I have an 87, which I'm going to approximate to a 9. Now, I don't need the E bar, I need the probability of E. I need the probability of at least 1. So, the probability of the event E is 1 minus the probability of the complement. So therefore, the probability of drawing at least 1 heart is 1 minus 0.4219. 1 minus the answer is 0.5781.